Welcome back, everybody. Now we're ready to talk about section 8.2, where we'll focus on estimating population means. Now that we've talked about the distribution of sample means, we're going to be able to use that to estimate population means. The bottom line is that when we deal with sample data, our population estimates are never going to be perfect because when we're dealing with sample data, we're dealing with incomplete data. So we're going to learn how to compute margins of error and then confidence intervals. Those margins of error and confidence intervals will provide us with a range of values likely to include the population mean. So let's jump right in, start talking about estimating population means. If we had a single random sample from a population, so just one random sample, we can compute a mean for that sample. And that sample mean, x bar, if we had to pick one value, would provide our best estimate of the population mean. Because really, what other data do we have? So based on that sample data, if I computed a sample mean, that would probably be my one best guess for what the population mean is. But we need to recognize that sampling error exists. And recall that sampling error is just that difference that we find between a sample mean and a population mean. So even though x bar would be our best estimate of mu if we had to pick one value, we would have very little confidence that it's exactly equal to that population mean. And that would leave us wanting a better strategy. So what we're going to do is create what's known as a 95% confidence interval. And that confidence interval is likely to have a value within its range that contains the true value of mu. So the bottom line is, instead of picking one value, like the sample mean, to estimate the population mean, we'll come up with a range of values or an interval of values that is likely to contain that true value for the population mean. So in other words, we're going to look at 95% of all the possible sample means. And the way that we're going to do that is because we know, due to the distribution of sample means, that within two standard errors, 95% of all sample means will fall. So what we'll do is we'll start with that sample mean, and then we'll add and subtract two standard errors to and from that value. That will leave us with 95%, a range that contains 95% of all possible sample means. So once we put this together, you'll see it'll make a little bit more sense. Let's look at the formulas that we're going to use and the notation. When we compute the margin of error, in our formulas, you'll just see an E representing the margin of error. So that just represents error, essentially, the margin of error. And what the margin of error is going to represent, as I was discussing right here, is two standard errors. Well, you might recall that the standard error was looking at the standard deviation, either written with an S for the sample standard deviation or a sigma for the population standard deviation, divided by the square root of n. Well, we're multiplying that by 2. So the margin of error is representing two standard errors or two standard deviations. So what we will do then to compute our 95% confidence interval is take our sample mean and then add and subtract those two standard errors. So those two standard errors are computed within the margin of error. And remember, E represents the margin of error. So essentially what we're left with is a two-step process. We first compute the margin of error using this basic formula, and then we compute our confidence interval by adding and subtracting that margin of error, plus and minus, adding it and subtracting it from our mean. So if you want to look at it graphically, it'll look something like this. Our sample mean starts in the middle, and then we add the two standard errors, and we subtract the two standard errors. So then we'll say within this range of values, the population mean is very likely to fall. In fact, within these two values, the probability is 0.95 that the true population mean will fall. So it's a very high likelihood. Let me show you somewhat differently. Theoretically speaking, if we were to obtain many more samples and create confidence intervals for all those samples, 95% of those confidence intervals would contain the true value of the population mean. And that's what we're trying to estimate, the value of the population mean. We're trying to find that value based on our sample data. So this is just showing, let's say we collected data and we found that the sample mean was equal to this value right here. We can compute a confidence interval where we're going to add the margin of error, we're going to subtract the margin of error, and within this range right here, the probability is 0.95 that the true population mean will fall. And this line right here is representing the true population mean. The black dots are representing the sample means. So all of these values in here are sample means that were below the true mean, and all of these sample means on this blue side are values that were above the true population mean. But we can see here that these confidence intervals are typically including this true population mean value. So out of these 20 times, 19 times those confidence intervals contain the true population mean value. There was just this one time right here where this sample mean was relatively high, and when we subtracted the margin of error and added the margin of error, this confidence interval right here did not contain this true mean value. Well, that's going to happen about 5 times out of 100, or in this case, 1 in 20. So in other words, about 95% of the time, our confidence interval will contain the true value for the population mean. So that's very powerful. We're able to use that sample data to estimate a value for the population value, the population mean in this case. So that's why we're going to be able to conclude, kind of using the terminology that we use, that we're about 95% confident that our interval will include the value of mu. So that's one reason why we call it a 95% confidence interval. All right, let's go through a quick example, kind of walking through this. In this particular case, I'm gonna give you the value of the margin of error. This is just to get us started, and in the next example, we'll compute that and then put it all together. So imagine this example. Researchers found that the average time spent by 8th graders watching TV is equal to 6.7 hours per week, with a margin of error of 0.4 hours. And that margin of error is computed for a 95% confidence interval. So construct and interpret the 95% confidence interval. And again, this is the notation that we will use to show a 95% confidence interval. So here's our solution. We're going to take our sample mean, which we have right here, and then we're simply going to add, subtract our margin of error. So we're going to have an upper confidence interval limit and a lower confidence interval limit. So let's look at our confidence interval for the upper portion. Sorry, my pen doesn't always write really well. So again, we're just going to follow our formula. We're going to take our sample mean, x bar, that was equal to 6.7 hours per week. So we have 6.7. And then to that, we're going to add and we're going to subtract the margin of error. Well, we're looking at the upper confidence interval portion at this point. So let's add the margin of error. So we're going to add 0.4 hours. So in this case, 6.7 plus 0.4 is going to equal 7.1 hours. Let's compute the confidence interval for the lower portion. In this case, again, we're going to start with the sample mean, 6.7, and now we're going to subtract the margin of error. So you see, we're using that sample mean to find a range of values that we believe includes the true population mean. In this case, 6.7 minus 0.4 is going to equal 6.3 hours. So how do we interpret this range? The bottom line is the probability equals 0.95, or we can be 95% confident. There are a couple different ways to interpret this. In reality, we're computing something based on probability. So the probability is 0.95 that this range is going to include that true population mean. Some people like to view it in terms of confidence. I see that as more of a psychological issue, but I can see also how confidence maps onto probability. So the probability is 0.95 that the population mean time spent watching TV. For 8th graders is between 6.3 hours and 7.1 hours per week. All right, so there are really, I guess, 3 important components of this interpretation. And these three components are important to demonstrate, like on an exam, for example, that you are really understanding what we're computing. One, we're computing a 95% confidence interval. So in the interpretation, we have to make sure we're saying something about the probability. I mean, a 95% confidence interval is different than a 10% confidence interval. Because if I'm saying the probability is 0.95, that my range is going to include that true population value, that's different than saying I'm just 10% confident. So this is a high confidence level. So that's one important component. The next thing that's important is, what are we talking about? What are we really trying to estimate? So in this particular case, I'm making it clear that we're saying we're 95% confident that the population mean time spent watching TV. So that's the population mean I'm talking about, and that's always represented by the sample mean. So this sample mean represents 6 hours per week watching TV for the sample. I want to figure out, what does that represent for the population? What's the population mean time spent watching TV? That's what I'm trying to learn about. Population mean time spent watching TV. And then of course I need to list what the values are in my confidence interval. So those three components are necessary for any valid interpretation. The math is obviously very straightforward. Let's go through another example, and in this example we'll compute the margin of error. So compute the margin of error in the 95% confidence interval for a sample of 267 men who have an average protein intake of 77 grams. So X bar is representing the sample mean of 77 grams with the standard deviation of 58.6 grams, and S represents a sample standard deviation. So let's look at our solution. First, we want to compute the margin of error. And when we're dealing with sample data, it's essentially an estimated margin of error. So our estimated margin of error is going to equal 2 times the estimated standard error. So we're not computing anything new here. Let's go ahead and work it out. So we're going to take 2 times our standard deviation, that's 58.6 grams. Then we need to divide that by the square root of our sample size. In this case, our sample size equals 267. So the square root of 267. So let's go ahead and work that out. I think we're going to need some help with our calculator. So let's look at our numerator. We've got 2 times 58.6. That equals 117.2. So we've got 117.2 divided by, let's find the square root of 267. So we'll take 267 and we will hit our square root button. That equals 16.34. Okay, so 16.34. All right, let's just work that out real quickly. So we're going to take now 117.2 and divide by 16.34. So our margin of error equals 17.17. 17.17. 17.17. All right, well, now that we know our standard error, our margin of error, which is based on our standard error, this is the formula that I'm highlighting right there for the standard error, and you see we multiply it by 2. So our margin of error is now going to be added and subtracted to and from our sample mean. So let's compute that confidence interval. So let's first compute the upper portion, upper, of our confidence interval. We're going to take that sample mean of 77 grams and then add 17.7. Let's see, 77 plus 17 would equal 84. So we have 84.17 grams. And now let's compute the confidence interval lower value. That's going to be 77 grams minus 17.17. Let's see, 74 minus 17, that equals, it's going to be 69.83. Yes, that looks right, 69.83. And of course, we can verify with our calculators. Let's go ahead and make sure that we can now interpret this like we interpreted the last one, making sure we understand there are 3 important things that we really want to focus on in our interpretation. So first of all, what's the probability? Well, we are computing 95% confidence intervals. That's a pretty high level of confidence. In other words, the probability is very high that our confidence interval will contain the actual population mean. So the probability is 0.95. Or we can be 95% confident. that so what are we really trying to learn about? I collected data from a sample to figure out something about the sample mean number of protein grams that they take in. So I'm trying to learn about the population mean protein intake. So I am 95% confident that the population mean protein intake for men is between 69.83 and 84.17 grams. All right, that's it. So the probability is 0.95 that the population mean protein intake for men is between 69.83 grams and 84.17 grams. And again, we were using sample data. So this sample data, this sample mean that came from these 267 men to learn something about the population mean. So this is inferential statistics at its best. Here's a really neat example. And this is going to help you understand, too, about what we talk about when we talk about statistically significant differences. This is just going to give you a glimmer about what that's all about coming up. A study examined body temperature in 106 subjects. So that's our N, that's our sample size. The average temperature, X bar, was equal to 98.2 degrees Fahrenheit with a standard deviation of 0.62 degrees Fahrenheit. So, of course, not everybody had exactly the same body temperature. There was some variability. Standard deviation measures that variability. But the sample mean was equal to 98.2. Estimate the population mean body temperature. Well, one thing that makes this interesting is most of us have this idea that an average body temperature is 98.6 degrees Fahrenheit. So this is a little bit lower. You know, I mean, is that something that we would expect just by chance? Well, let's compute our confidence interval. Let's see if our confidence interval includes 98.6 degrees. Because if it would, then that's the type of sample mean we would expect just by chance. But if it doesn't include that value, of 98.6 in the confidence interval that we compute, then we'd see that, wow, we found this really low value. We'd have actually statistically significant differences. So that's something that we'll talk about more formally coming up. But this confidence interval that we compute will provide us with that information today. So let's just go through what we've learned, and we'll see how this all fits in. So first, if we're going to compute a confidence interval, we have to compute the margin of error. And then once we compute the margin of error, we're going to stick it in to compute our confidence interval. So we're going to start right here. So we're going to take 2 times the standard deviation, which is equal to 0.62. So 2 times 0.62. And then we need to divide by the square root of our sample size, which in this case is 106. So let's focus on the numerator. We'll take 2 times 0.62. 2 multiplied by 0.62 equals 1.24. So we've got 1.24 divided by, let's find the square root of our sample size there. We want 106, and I'm going to take the square root of that. That equals 10.295. We'll call that 10.30. 10.30. All right, let's just do the math on that real quickly. We've got 1.24 divided by 10.3, and that equals 0.12. So our margin of error in this case is just 0.12. It's a relatively small value. Okay, so we're going to take now our sample mean, which is equal to 98.2 degrees Fahrenheit, and compute a lower value and an upper value for our confidence interval. So CI, let's do our lower value, is going to equal our sample mean of 98.2 degrees minus, I guess I'm doing the lower one first, minus our margin of error, 0.12. And that's going to equal, let's just work that out with our calculator real quick, 98.2 minus 0.12 equals 98.08. 98.08. Now let's compute our upper value. Of course, it doesn't matter if you compute your lower or your upper first. Upper value is going to be 98.2 degrees plus 0.12. So plus our margin of error of 0.12. So in this case, that's going to equal, and again, let's just use our calculator to make sure we don't make a mistake, 98.2 plus 0.12. That equals 98.32. 98.32. All right, let's interpret that. And when we interpret it, we'll try to make sense of the whole 98.6 thing, and we'll put that in perspective. So again, there are three important things that we need to think about in our interpretation. We computed a 95% confidence interval. So that's based on a probability of 0.95. So the probability is 0.95. We can be 95% confident that the population mean body temperature is between 98.08 degrees Fahrenheit and 98.32 degrees Fahrenheit. That's pretty interesting. I mean, we're saying the probability is 0.95. That's a high probability that the true population average body temperature is between 98.08 and 98.32. You'll note that 98.6 degrees Fahrenheit is not within that 95% confidence interval. So in this case, what we're going to learn, and we'll formalize this later on, is that we would have statistically significant differences. So the data that we collected from this sample provided us with a sample mean of 98.2 degrees Fahrenheit. That does indeed statistically significantly differ from 98.6 degrees Fahrenheit, which is what we come to typically believe to be an average body temperature. So based on this data right here, we would have some evidence that the true population average body temperature is actually lower than 98.6 degrees Fahrenheit. So again, this confidence interval provides us with a lot of information helping us estimate the true population value just based on our sample data and our sample mean, which was based on these 106 subjects. Let's close our discussion by talking about sample size real quickly. When we plan studies, we often know the margin of error that we'd like to have, and we can estimate sample size that's needed to ensure that margin of error. And the way that we can do that is just by taking the formula that we have for margin of error and rearranging it so that we can solve for n. So this has all the components of the formula that we looked at before that was based on the margin of error, but now we've just reworked it so that it's solved for our sample size. Now, when we know the population standard deviation, we can use this formula, but we don't typically know it. So we typically have to compute our n, an approximate value, based on substituting our sample standard deviation. That's no big deal. Let's go through a couple examples real quickly, and you'll see what I'm talking about here. So let's say you plan a study looking at housing costs, and you want to provide a 95% confidence interval estimate. So you're trying to learn the true value of these housing costs based on sample data. So we can do that by computing a 95% confidence interval. And let's say that previous research suggests that the population standard deviation equals $7,200 in this particular case. So what sample size will ensure that your sample mean is within $500 of the true population mean? So we want the price that we come up with when we're talking about like housing prices to be within about $500 of the true population mean. So what sample size are we going to need to ensure that our sample mean is within that value? All right, well, all that we need to do is use our formula here. So we're going to take 2 times the standard deviation. So here we're going to have 2 times our standard deviation, and our standard deviation in this case equals 7,200. 7,200, and we're going to divide by our margin of error. We want to be within $500. Divide by $500, and we have to look really closely at our formula. We need to square that value. So I need to take this whole thing then and square it. All right, so let's just kind of work from the inside here. Let's multiply these two things out real quickly. 2 times 7,200 is going to be 14,400. So we have 14,400 divided by 500, and we still need to square this. So put it back in parentheses and square it. Let's just work out our fraction real quickly. Pull out our calculator again. So we've got 14,400 divided by 500 equals 28.8. So we have 28.8. We still need to square that. So let's do that and finally be done with our answer. 28.8 times 28.8. That equals 829.44. 829.44. So what that's essentially telling us is our sample size would need to include 829.44 data points. And here we're talking about housing costs. So we would need to include 829.44 housing prices in our sample for our sample mean to be within $500 of the true population mean when we compute our confidence interval. Well, of course, we can't have a fractional component when we're looking in our sample to include housing costs, so we would round that up to a sample size of 830. Well, let's just play some games with the numbers for a second. Let's say that we actually wanted our margin of error to be less. So what sample size would ensure that our sample mean is within $100 of the population mean? So now we want it to be much closer. We want there to be much less variability in our data. Let's see what would happen. And what I want you to do as we're kind of talking about this here is just predict. Do you think the sample size is going to go up, or do you think the sample size is going to go down? Because what I'm saying here is I want my sample data now to come closer to the true population mean. Do you think that's going to require more data or less data? A larger sample size or a smaller sample size? Let's compute it. So again, we're going to use the same formula. In this case, we're going to take our 2, multiply again by our standard deviation, 7,200. And now we're going to divide by that new margin of error that we're looking for. So we want our margin of error to be smaller in this case, 100. So we're going to divide by 100. So once we compute that, we have to take that whole thing and square it. All right, so let's simplify and solve it. Again, 2 times 7,200 is going to equal 14,400. We're going to divide by 100 and then square that value. 14,400 divided by 100 is going to equal 144. So we've got 144, but we still need to square that. 144 squared. Let's compute that really quickly. So we'll take 144 and multiply by 144. That equals 20,736. 20,736. So here we're learning that our sample size would need to include 20,736 home prices in our sample in order to have a margin of error of just $100. That's a really large sample size. So there are some things that are kind of interesting that come from this. Let's first just kind of look at our interpretation. To ensure that our sample mean is within $500 of mu, we'd need to include at least, there was 830 home prices in our sample. To be within $100 of that population mean, we would need at least 20,736 home prices. 20,736 home prices in our sample, which is really a large sample. So it's kind of interesting what you see here. If we're trying to go from a margin of error of 500 down to 100, we're talking about a factor of like about 5 right there. But look at what we're dealing with here in terms of the number of subjects needed. Here we'd be going from needing 829 to needing 20,000. That's a factor of approximately 25. All right, so do you see how there are diminishing returns? So accuracy, we learn, comes with disproportionately high costs. If I want to be much more accurate in my estimate, and here we can see that we're being about 5 times more accurate in a sense if you look at going from 500 to 100 for our margin of error, it's going to require 25 times more data. So that's what I mean when I say accuracy comes with disproportionately high costs. So that's why people need to be reasonable when they do their research studies and pick a sample size that is within reason. I mean, we usually can't collect that much data. This time out to think section, discusses the quandary that we were just in, where I was asking, do you think we're going to need more data or less data? And you can imagine this could be an essay question on an exam. If you decide you want a smaller margin of error for a confidence interval, should you increase or decrease the sample size? And why? Briefly explain your answer. And here would be a great example. Mathematically speaking, as n increases, our standard error decreases. We learned that long ago. As our sample size increases, standard error decreases, and thus our margin of error is going to decrease. So remember, standard error is simply based on our standard deviation divided by the sample size. So if we're dividing by bigger and bigger and bigger numbers, our standard error is smaller and smaller and smaller. Well, if we're multiplying 2 times our standard error, that means our margin of error is going to get smaller, mathematically speaking, as our sample size increases. And then conceptually, think about it this way. As n increases, each sample is kind of coming closer and closer to measuring the population. So we would expect that our sample means would come closer and closer and better, they do a better and better job of representing mu. So mathematically and conceptually, we're understanding why a larger sample size is going to result in a smaller margin of error. So this is the type of response that would get a really good grade on an exam. That, my friends, is the key content from section 8.2. For now, that is all.